Hey guys, welcome back. We're gonna go ahead and finish up the chapter here via video because I'm out judging a science fair right now. So this will be reasonably quick. There's not a lot left in the chapter. I'm gonna have questions embedded in this video. You have to answer the questions, and I'll give you a grade from those questions. So we left off last time talking about yawning. A couple of source citations. If you get done with the video early, you can go back and check those out. Whether yawning is caused by decreased oxygen levels to the brain or to cool the brain. There's some disagreement there, but both the articles are actually rather interesting. So here's your respiratory volumes chart. This is the lung volume in milliliters, how many milliliters of air in the lungs. And so you can see the tidal volume. That is inhaling, exhaling, inhaling, exhaling, inhaling, exhaling. Inhaling, of course, you're going to get close to 3,000 milliliters, or we can basically say 3 liters. And exhaling, you're at about 2.5 liters. And so the actual volume of air you're moving is not too much, half a liter. You could think of about how big that would be from a plastic bottle. So that's your tidal volume is about half a liter. If you expire as much as you can, so you exhale as hard as you can, that is your ERV. Your expiratory reserve volume is below this dotted line, which is tidal. And what's left over, that's called your residual volume. So you always have about a liter, maybe a liter and a quarter of air in your lungs. That's going to vary with the size of the person, of course. Bigger people, taller people have bigger lungs than shorter people. Now here we go back to tidal volume, and we breathe in as much as we can. And you can see we can almost get 6 liters of air in this example, which is really rather impressive. And so we breathe in as much as we can, and that is your inspiratory reserve volume, is the distance above tidal. As much as you can breathe in addition to tidal, is your IRV. And so then you can go back to tidal, and if you breathe in as much as you can and breathe out as much as you can, we call that the vital capacity, which is if you had to, how much air could you possibly move, and that is the vital capacity. So all of these together is the total lung capacity. So your IRV, your ERV, and your residual volume all together makes a total lung capacity. We never empty that residual volume where the lungs would collapse, and that would be rather unfortunate. But the total lung capacity you can see here is very close to 6 liters, which is quite a lot of volume. So we've been talking just about breathing, inhaling and exhaling, but there are several non-respiratory air movements that the respiratory system will carry out. Coughing, for example, sneezing, laughing, crying, hiccuping, yawning, and of course speaking. You have to regulate how much air is in your lungs the whole time so you can carry out a sentence without stopping in the middle and going or something like that. Hiccuping real quick is an interesting one because what causes hiccups is a spasm in the diaphragm, and it sort of works like when you're sitting at a table writing and you notice that your arm is kind of twitching and it's sort of a random twitch. Your diaphragm can do that, and when it does, it sort of pushes air out in weird little spurts. And that's what actually causes hiccups. Odd thing, men get hiccups more often than women do. So there's that. Factors affecting breathing. This is a really cool diagram. You have the lungs on the outside, the heart, which you're very familiar with, the aorta, and branching right out of the aorta, the common carotid, which you already knew. Now, inside the carotid artery are some little sensory bodies that connect to the nervous system. And those sensory bodies are maintaining an input of information with how much oxygen is in the blood and how much carbon dioxide is in the blood, and they can sense this and they can send that up to the brain, primarily the brainstem, the medulla oblongata, letting it know how much oxygen and how much carbon dioxide is in your blood. This is the reason that it is difficult to hold your breath and you feel the urge to take a breath even though you're minutes and minutes and minutes away from actually causing brain damage or organ damage. You could hold your breath for much longer. But you get this urge after just 30 seconds or so to take a breath because it's the brainstem getting this input. So when you decrease the blood oxygen concentration, which happens normally, just from the blood flowing through your body and giving oxygen to the cells, you decrease the blood oxygen concentration in the blood. That was a little redundant, sorry for that sentence. You decrease oxygen concentration in the blood. That lets these little chemoreceptors in the carotid artery and in the aortic bodies, there's even little sensory bodies right here in the aorta, lets them know, hey, there's not as much oxygen as there should be in this blood. Would you please tell the brain it needs to take a breath? And that's exactly what it does. So that is the impulse or the urge that you are fighting when you want to hold your breath swimming underwater or something of that nature. So here's a really cool one. We have our diaphragm, this umbrella-shaped guy right here, our intercostal muscles, which you're familiar with, the lungs, and then we have nervous tissue embedded in the lung that branches out, and those end at what are called stretch receptors. And so this is kind of a cool deal. When the motor impulses travel from the respiratory center to the diaphragm, so that means basically we've got the input from the carotid and neurotic bodies that said, hey, we don't have enough oxygen, brain, do something about this, and brainstem goes, you got it, let's take a breath. And it sends the motor impulse down the spinal cord, it branches out into the lungs, and it stimulates the muscles, the diaphragm, the intercostals to go ahead and contract and expand those ribs. And so that's what they do. They contract, they expand the ribs, and the lungs expand to fill that void, which we talked about with some really basic pressure laws from chemistry that we learned. And now, when those expand out as far as they ought to, they stimulate these stretch receptors, which are just nerve endings. And those stretch receptors send the signal that the lungs have indeed taken their breath. They've expanded out as far as they should. And these inhibitory impulses from the receptors to the respiratory center prevent overinflation of the lung. So it's kind of like a negative feedback thing where the brain stem and the spinal cord says, lungs expand, the lungs expand. And then these little nerves, little stretch receptors say, okay, brainstem, spinal cord, stop. The lungs have expanded enough, and the brain stops. So it's not just muscles, and it's not just air pressure. This is carefully, carefully regulated with nerves, exactly how much space we allow those lungs to fill. So as with anything, the more you know, the more complicated the world becomes, but that's okay. So what affects your breathing rate, both how quickly you breathe and the need to take a breath, or that perceived need. When you hold your breath, you start to get a higher concentration of carbon dioxide. This PCO2 means the partial pressure of carbon dioxide dissolved in the blood. And you can sense that in those aortic and carotid bodies we already talked about. And it's also going to cause another thing that's not so good. CSF is cerebrospinal fluid. It is the hopefully clear fluid that is flowing around the brain and down the spine. And as you hold your breath and that carbon dioxide starts to accumulate, this takes a while, but it will actually change the pH. It will increase the hydrogen ions in that cerebrospinal fluid, and it will start to make it just a little bit acidic. And those two things interact with that aortic and that carotid body to say, hey, we really need to take a breath right now because we've held our breath to a point where we are actually becoming acidic, and that's not okay. So then alveolar ventilation increases, which is, meaning you're going to take a deeper breath or more breaths. As you do that, the CO2 levels decrease because by passive diffusion, they are moving the CO2 out to the alveoli. When that happens, the hydrogen ions decrease, so we become just a little less acidic, back to the pH that we want to be at, and that tells the brain that everything's cool now. So we've looked at alveoli before, these little grape-like clusters at the end of the bronchioles of the lungs. And one cool thing to know about alveoli is that they are not just like a grape and that is the end. They have little holes called alveolar pores, and they are holes that allow oxygen and carbon dioxide, the whole 9 yards, nitrogen, everything that's in the air, to pass from one alveolus to another alveolus to another alveolus if need be, to ensure that the air is getting really good exposure to those capillaries. Alveoli are not a dead-end road. They are a little bit more like a honeycomb. And so think about it like when we did that lab and you're punching holes through that cardboard tube. There's lots of ways for the air to get where it needs to be. That's sort of what pores in the alveoli are like. So that's a pretty cool structure. Now, if we look at the alveolus, we say, okay, this is one alveolus. And we take the pores out to make it a little bit simpler. There are cells in here, and they have a couple different jobs. The type 2 cell is a surfactant secreting cell. And so this fluid all around that alveolus is going to maintain very, very low surface tension. If you have too much surface tension, the alveolus will want to stick to itself, and that would cause very poor respiration. And so when we secrete a surfactant, think of like soap. It decreases that surface tension, it makes it slippery, I guess, and the alveolus can stay inflated, and it won't stick to itself, and it won't stick to other parts of lung tissue. So surfactant is very, very, very important for an alveolus to function as it should. Then you have a type 1 cell, and you don't have to remember type 1 or type 2. That's not a memory thing. I just want you to know how it works. There's squamous epithelial cells. That's what makes up the alveolar wall, is simple squamous cells. And so this is an alveolus kind of cut in half. See, there's one cell, and it ends right here where we've cut it open to see that nucleus. And there's one cell, there's one cell, there's one cell. And then you might find macrophages in the lungs, which of course are white blood cells that are cruising through the lungs, eating up bacteria, viruses, foreign particles. You know, not everything that you breathe in is captured in the nose or in the mucus in the trachea. Some things are going to make it to the bottom of the lungs. And when they do, we need white blood cells down there to consume those things and to keep us healthy. You know, you have to fight infection in the lungs as well, right? So here's something that we've looked at before. We just kind of threw some data in there now. So this is the capillary vessel. It's deoxygenated here and it is oxygenated here. This is the alveolus. So when you breathe in, the oxygen partial pressure is 104 millimeters mercury. There's a lot of oxygen in the air. And the carbon dioxide partial pressure is very low. It's only 40. Now the venous blood that is coming from the right ventricle, the heart, its partial pressure of CO2 is 45 millimeters of mercury. So what that means, a simple diffusion tells us if we have 45 as our pressure for CO2 here and 40 for our pressure of CO2 here, we will move down the pressure gradient to an area of less pressure. That's how we get carbon dioxide out of a capillary. Now the oxygen is coming in very similar at 40, but what you're breathing in is 104. And so that 104 is much greater than 40, and so the oxygen is going to flow into the capillary just down the pressure gradient, or down a concentration gradient, you could even say. These units just happen to be in pressure. And so that's one reason that, like in the lab we did, where you're able to take multiple breaths out of a 1-gallon bag, is because in one breath you don't actually extract all of the oxygen. 104 is much greater than 40. So the first breath, you might take that oxygen concentration down to like 90. And the next breath, you take it down to 80. And you know, you'd have to continue on for multiple breaths before you completely deplete it. And so if you got a perfect exchange, which I don't know if it's really perfect, they say, you know, 40 gets in for CO2 and all of 144 gets in for oxygen. I don't know if I really buy that it's that clean cut, but it gets the point across, I guess. So once the oxygen is in the blood, it is going to bond to hemoglobin, which you probably already know. Hemoglobin is a pigment in red blood cells. It's what makes blood red. When the iron in hemoglobin attracts oxygen in the air, it bonds and it turns red for the same reason iron oxide turns red when an old vehicle becomes rusty. It's very similar to the reason your blood is bright red. And so hemoglobin bonding to oxygen forms a new pigment we call oxyhemoglobin, which really just means hemoglobin bonded to oxygen. And oxyhemoglobin releases the oxygen when it's in the body cells that don't have enough oxygen. So when it makes it to the tissues that it's trying to carry this to. There's still plenty of oxygen left in that hemoglobin when it's in venous blood. It's not like it offloads 100% of the oxygen to these body cells. There's still some left. And so here's the example of that oxyhemoglobin taken off. It gets to cells where the oxygen pressure is 40. Here it's 95. So it offloads some of the oxygen, but not all of it, until there's about an equal pressure of oxygen on both sides. Now we're at 40, and we're going to go ahead and take this back to the lungs because there is still oxygen in it, but it's not enough to get cells a lot of oxygen by simple diffusion. So we just keep moving it to the lungs and get it pumped up back there to 104 hypothetically and run the whole cycle again. So know that hemoglobin does not offload its entire cargo of oxygen, but it does enough to get us to, I guess, a state of equilibrium with regards to gas pressures in a liquid. So carbon dioxide is a little different. Hemoglobin is easy because hemoglobin grabs the oxygen, takes it where it wants to be, drops the oxygen off, end of the story. Carbon dioxide is a little bit trickier because carbon dioxide is actually dissolved in the blood plasma. That's the fluid portion of blood, which you probably already know. It can sometimes be combined with hemoglobin, but it will be in the form of bicarbonate ions. And so here you have cellular carbon dioxide. The cellular carbon dioxide is given off into the blood, and it can dissolve in plasma to a certain point, and then it will get into hemoglobin, and it will combine with hemoglobin to make carbaminohemoglobin, which is a crazy word, and you don't have to remember that. And other times it will become HCO3, which is bicarbonate, and that bicarbonate combines with hemoglobin to make H2CO3. And so that can travel through the blood that way, but because it has extra hydrogens bound to it, bonded to it rather, it can make the blood acidic if it's not regulated. So you do need to exhale that carbon dioxide in the lungs, or else it will make what I believe H2CO3. You could Google this and prove me wrong. I think it's carbonic acid. And so too much carbonic acid would be a bad deal. But you can fact check me on that. That doesn't hurt my feelings. See if I'm right or if I am a crazy person. So, as always, we end each chapter with the somewhat depressing note of how organ systems change with age. As you change over your lifespan, the lungs are going to reflect the accumulation of environmental influences. If you live in a city with a lot of smog, or you are a worker carving Mount Rushmore, breathing fine granite dust for years, that's going to show up in your lungs as you age. It's going to reflect the aging of other organ systems as well. Your cilia become a little less active, so you're going to accumulate a lot more mucus. To make that problem worse, the mucus that's already there actually becomes thicker, so swallowing, gagging, and coughing reflex is slow. Macrophages in the lungs become less efficient, so you're not able to fight infection, and pneumonia becomes a really serious problem as you become older. And you increase susceptibility to respiratory infections, and the students say, no duh, if the macrophages don't work, you're probably going to get infected. You may develop barrel chest. Bronchial walls can thin and collapse, and you will get a bit of dead space, which is space in the lungs where the thoracic cavity where the lungs don't truly expand to or fill to. So the last thing is a clinical application, and that is the very obvious effects of cigarette smoking on the lungs, which I'm sure you've all learned about in middle school. If you smoke, this is lung tissue with a tumor on it here in this picture. The cilia disappear if you smoke. It produces excess mucus. The lung congestion increases the lung infections. There's all sorts of cool diseases you're going to get from smoking, like COPD, emphysema, lung cancer is at an 85% mortality rate, so that's kind of a tough one to roll the dice on. All sorts of stuff like that. And you get thickened bronchioles lining, so you're not going to get as much air in as you should be. The bronchioles also lose their elasticity, so they're not able to kind of perforate out in that lung tissue like they should be able to. Emphysema becomes 15 times more common, and I mean, that's fascinating. If for nothing else, you can suffocate while you're on pure oxygen and go out that way. So, I mean, it's interesting. You got to give them some credit there. And a lot of that damage can be repaired when smoking stops. It kind of depends on how long you've been smoking, because they have a lot of known carcinogens, and once that DNA is damaged, you're going to be in a world of hurt. But definitely the effects it has on like blood pressure and those sorts of things, stroke, that kind of stuff. When you stop smoking, those effects actually clear up really fast. So I hope you're not smoking, of course, but if you are, please stop. It'll make your life a whole lot better. So with that, I'm pretty certain that's a chapter. So thank you for your time.